All right, now you can bail from YouTube. All right, so share screen, whiteboard. How do I know when my displacement is maximized? That's the question at hand. If I have a velocity function, I'm looking at when, by looking at the velocity equation, the question is, when do I know that I've gone as far away as possible? Anybody have a possible answer to that question? Go ahead. When velocity is zero. That's a really good place to start. And it could, well, those are the places to look, I'll say that, right? So if you think about, I have a velocity function, its antiderivative is a position function. When do I maximize that? I take its derivative and I look at where that's equal to zero, and that's where velocity is zero, right? So if I'm thinking about, I'm going to walk across the room, I walk, I have positive velocity, say, I come to a stop, and then I back up. As I'm backing up, my velocity is negative. So the farther away I went, is the farthest I went away was when my velocity is zero. Is everyone okay with that statement? Okay. And so I can look at a graph and start to think about where is my velocity zero, and think in terms of where is it maximized. Now, I'll share let's see here. Here's the text for us. So here's an example towards the end of that section. And this is where things get a little bit different. So you can see that one graph right there. And the question is basically that I will ask, it's slightly independent of the example. If we're started off at zero, you know, where is my velocity maximized? Well, at first, my velocity here is negative. So what does that sort of mean to me? So you're going backwards, right? And so I ended up having because the area in the curve talks about displacement, I ended up backing up 11 units, right? And then I go forward 38 units. But now, in some sense, my displacement is maximized, if you will, by the fact that I've gone back 11 units, and that's where the velocity is zero. And then I go forward 38. So now how far away am I from where I started? 27, right? Negative 11 plus 38 gives me a certain maximum. And then I back up another 11, right? Does that make sense to everybody, how that plays out? Okay, so I don't remember who even asked the question to start, but the question was, how can I tell about where my maximum displacement is? You effectively do look at where your velocity is zero, but you got to keep track of what other conditions are going on around you. Does that help? Other questions from the homework? All right, so we're going to go back to the whiteboard here on our overhead screen and whatnot, and then we are going to start off with a bit of review of what we were talking about last time, and then we didn't finish our problem, okay, that we were working on. So here is my review. We had a velocity function, v of t, and that was negative 32t plus 64. And then we figured out a position function. That position function was s of t. And we found that through an antiderivative in an initial position. The initial position s of 0 was supposed to be 0. So we found s of t was negative 16t squared plus 64t. Right? That sound familiar? Now, question B that we posed last time, B says, where is what's the maximum height of the ball, maximum displacement of this ball? And we said, well, S prime of 2 is equal to 0. So that's where the velocity is 0. So that led us to say, well, then S of 2, this is velocity equals 0. S of 2 we found out was 64 feet. Everyone okay with that? That's where we ended. So new problem to ask, this is part C. It simply asks, what's the displacement at t equals 3? And how do I figure that out?
You plug the 3 in for t.
And when I plug it into which equation?
It should be the s of t.
Right, I plug it in. So displacement when t is equal to 3, I've done all the hard work already. I found my position or my displacement function. So now I just plug it, s of 3 is equal to negative 16 times 3 squared plus 64 times 3. And then that is negative 144 and 192. This is 48. Everybody all right with that?
So that's what the displacement is.
That's the displacement. So in this case, the ball has gone up to its peak at 64. It's begun to fall back down, and it's fallen back down for 1 second. And now it's at a height of 48 feet. Pretty good. Questions? Yes.
Under what circumstance would you ever plug in 3 to the original VFT equation?
If I asked you how fast I was going when t equals 3, or my velocity, yep. Anything else? All right, so we're going to say here, next slide. I'm going to write that down, of course, but the thing that you're going to want to talk about now is going to be same questions, same answers, and a different method. All right, so that's what we're going to come up with. Our answers from before were 64, 64, 48. What's my initial velocity? 64 feet per second. What's my maximum height? Coincidentally, it's also 64 feet. That I don't think there's a pattern there. And then last one was 48 feet, okay? But now we're gonna have a new method of actually getting these answers. And this, again, ties into the big ideas of calculus, ties in what section 5.2 is really all about. So I can draw some axes here. I'm going to draw a v of t, and I really only care about when I get to t equals 3, but I'll give myself 4 spots here, 1, 2, 3, 4. And then I'm just going to arbitrarily say this is 64 feet here, and then by symmetry, this is negative 64. And then my velocity function starts at 64, goes down with a slope of negative 32. So I know it's going to go through this point here, and it's going to end up going through this point down here as well. So I'm just going to draw it as best as I can with a pad, and bam, nailed it. And this is my v of t function. Everybody all right with that? That's negative 32t plus 64. So A is initial velocity. Well, I can see that that's my y-intercept, right? So 64 feet per second. That's a 4. Well, it looks like a 9. There we go. All right, second question, B. is my max height slash displacement. Question beforehand, class, was how do I find my maximum height displacement? Where do I go? How do I know where to look? And the answer was, oh, think about where velocity is 0, right? So now this is the thing that we hinted at the beginning of class on Friday. This is where our introduction came in. And now is our first chance to actually put it into practice. Oh yeah, there's an area under the curve aspect of this. Notice, what's the area of this triangle right here? So this little 64, my pen's locked up. There we go. Maybe it's coming back. Oh, there we go. Got it. The area is, well, it's a triangle, 1/2 base times the height, right? 1/2, my base is base 2, my height is 64. That gives me 64 feet, right? And that matches the other thing, right? And so we hinted at this before. We said, oh yeah, if I understand that I have a velocity function, so its units in the vertical direction are feet per second, and my units in the horizontal direction are just seconds. So feet per second times seconds gives me feet. This gives me my 64 feet. I can answer the same question from last time just looking at my picture. That kind of cool? All right, so 64 feet is my answer over here. I'll put it in red. Jace, where's Jace? Can you tell the difference between the red and the blue?
Yes, red and blue I can.
Oh yeah, what kind of colorblind are you?
Red and green.
Red and green, okay. Should start messing with you now, right?
Please do. I'm excited about it.
All right, so that's my max height. And now part C was, what's my displacement at t equals 3, right? What's my displacement slash height at t equals 3? What am I going to do now?
On the area again,
For what part?
all the way up to 3 seconds.
All right, go all the way up to 3 seconds. And now let's use orange. So now here's my orange area. Well, what's the area of my orange triangle?
16.
So let's see here. It's 1/2. Well, the base is 1, and then the height. The height, well, that's -32, right? Halfway across there. So the height is, and then that's the issue at hand, is how do I deal with that? Well, the function value is -32 there. I can do -32, and this gives me this -16, right? We had a term for this on Friday. We said, normally when we're talking about area, we're only talking about positive numbers. But sometimes I want to talk about negative area, and I called it what kind of area? Signed area, right? And so this is a -16, and I'm okay with that. It's a -16 feet. And so then my final answer is going to be a 64 plus a -16, and that gives me my 48. Wow. Yeah.
So when we're saying area, it's not actually an area, it's just a distance. Because it's just in feet, not feet squared, correct?
So the area under the curve, the area between my function and the horizontal axis is going to correspond to a distance, right? So I'm finding that geometric area because it has the same number as the displacement, because I'm thinking about my units being differently. Instead of my units being a feet by a feet, my units are actually feet per second times a second. And I multiply that with that component analysis, is what you call it in engineering. Feet per second times seconds gives me feet, right? So it's a weird idea, but these areas do line up with the distance, if you will. Everyone okay with that? Any questions about this part? So now we hinted at it on Friday. We did a real simple example about something having constant velocity and then constant negative velocity, and all those areas lined up. We have this example here. This is supposed to be a big deal, though. It's like, wow, if I have a velocity function and I graph it, then the area underneath my velocity function is actually my displacement, how far I am from where I started. That's actually pretty cool, right? Meh. Yeah, I like it. I think it's cool. I didn't see that coming. It's like, oh, wow, that's pretty nifty. And back in the 1700s, people knew this. They just had a hard time finding areas. That was the real trick. Is that if I have a function describing something, how do I find this arbitrary area? All right. And then we're going to get to that soon. Not today, but we're going to get to that relatively soon. All right, so now we're going to make a quick transition. I'm going to show you something out of the text, just because it's spelled out there nicely. So here's our text. We're going to talk about the definition of a definite integral. You don't have to write this out word for word because it's in your book, right? But what I want you to know is this part here, basically. The definite integral of f. And I'm going to talk about the definite integral using this notation right here. The definite integral of f talks about the total signed area. All the area above the x-axis is positive. All the area below the x-axis counts as negative area. The integral is talking about the total signed area.
So that's basically what we're talking about here with when we found the second area with the positive plus negative.
Right. The answer to part C, I was looking for the total displacement. I was looking for my total signed area. Exactly. A different question would be like, in some sense, how far did the ball travel? It went up 64, came down 16. You can add those together, right? And that's a different question. It's the total displacement, which is the total signed area. Good. All right, real quick story on the side. That's not super important, but when I went to grad school, right? So I left undergrad at Liberty, a smaller school. I was doing well there. I was a big fish in a small pond. Went to Virginia Tech for grad school. Now I felt like I was in a big pond and I didn't know how I was going to stack up. I told you on Friday too that I fell in love with mathematics, this thing called abstract algebra. So when I went into school there, talked to my AC advisor, and they're like, well, there's two abstract algebra classes you can go to. One's the regular one grad students kind of go into when they don't really care about abstract algebra. But if you really love it, you can go into a more advanced class. And I was like, well, I really love it. I want to challenge myself. Let's go in the advanced class. He's like, you can do that. Just kind of know that the instructor is a little bit difficult. All right, whatever. I'm taking it. Day one, I was lost. I was scared, honestly. I thought, oh, I was wondering if I was a big fish in the big pond or a small fish. I'm definitely a small fish. I am out of my league here. And so very quickly, I was trying to get help, went to him a couple times for help. He was a nice guy, but I did not understand the help he was offering me, whatever. And so I started looking around the room, like, who do I go to get help with this stuff? Because I'm stuck. So saw this kid next to me. I knew him, Tyler. He was a first-year grad student, like I was, and he's taking notes. He's nodding his head, he's smiling, whatever. I'm like, okay, Tyler. Went to him after class. Tyler, help me out. I'm totally lost. He's all I'm lost. I have no idea what's going on. I'm like, dude, you're like nodding your head. You're doing these like, yeah, I do all those things so that he thinks I understand. Like, why do you do that? I don't know. So then I went to like person after person after person, like, help me. And they all said, I'm lost. I'm lost. Otherwise, we're all lost. But none of us are doing anything because we're all scared. And then we went from a class of 24-ish people, something around this size here, down to 6. Everyone kept on dropping out. And the only reason I didn't drop out is I was too scared to drop out. I thought if I dropped out of class and took like the easier class or just dropped, it was too late to get anything else, I was admitting that I was not cut out for grad school and I was on the fast track out of it all. So I thought I got to stick with this and make this work out. Turns out he was just a difficult instructor because I was a genius and I had no problem with everything else. But no, it was hard. The point of that story is whenever you think that you're like the one person who doesn't understand, high degree of probability that you're not the one person who doesn't understand. And then the person next to you nodding their head, whatever, faking it, totally faking it, right? And just ask your question if you're ever wondering, like, because no one wants to be the person, that guy who's slowing everything down. Don't sweat it. Just ask the question you want to ask. All right. So now moving on, let's make a new example and let's try to use this notation and get used to it a little bit. Okay. So back to our whiteboard, new slide. Here's a new example. Let's get the blue pen back out. I should just like pulling out the green and red pens and calling them different names, but they're whatever, and just telling you, here's a green pen, but it's actually the red pen. All right, so not that funny really. So here's our example. Let's, on the x-axis, let's get 5 units out here. 1, 2, 3, 4, 5. These are all straight lines, regardless of whether or not it looks super, super straight. Okay, so this is my graph of y as a function of x. So it goes over 2 units. The y is only plus or minus 1. Goes over 2 units to get to the max, then it cuts across the x-axis, straight line down, straight line back up. And then we have a bunch of questions we're going to ask over here. So as you're copying all this stuff down, go ahead and look at part A, which says the definite integral from 0 to 3 of f of x. What's that area going to be? Area under the big triangle, right? So I can do the 1/2 base times height, 1/2. What's the length of the base here? 3. What's the height? 1. So I should end up with 1.5, right? Square units, whatever my units happen to be. Correct, I did not. I didn't say this was a velocity function per se. We're going to evaluate the definite integral in a unitless fashion, if you will. You okay with that? Okay. All right, another example. What if I went from 0 to 2 this time? What would I have now?
It should be just half of what you had previously.
That triangle isn't quite symmetric, right? Yeah. So it's 1/2. What's the length of my base? 2. My height is 1. That gives me a 1. Everyone okay so far? All right, C says, what's the integral from 2 to 3 of f of x dx? It should just be 0.5, right? 1/2 times 1 times 1. Everyone all right with that? We're going to formally state this in just a few minutes, but here is an important concept that looks complicated when you write it out all mathy and stuff, but it's just common sense. The total area of this triangle is equal to the area of this one subregion plus the area of the other subregion, right? This 1.5 comes from the area of this triangle plus the area of this triangle. Not all that deep, right? And then mathematically, I realized, oh yeah, I can go from 0 all the way up to 3, or I can do it in like steps. I can go from 0 to 2, and then from 2 to 3, and it gives me the same answer. Everyone all right? All right, I think I have 2 or 3 more that I want to do. D, what if I integrate from 2 up to 4 of f of x dx? So I get an answer of 0. How do we get that? Yeah, so I have this 1/2 plus a negative 1/2, right? The part under the curve, are we okay with that? There's a certain amount of symmetry going on. We can kind of jump through it, but when it's all said and done, I can get a total signed area of 0. If I was thinking in terms of velocity, and this was my velocity function, I was going positive velocity in exactly the same way that later on I was going negative velocity. So it kind of makes sense. I just went out and back with a 0 displacement. All right. E, let's just go ahead and go from from 3 to 5 of f of x. And that gives me what?
Negative 1.5.
Not negative 1.5. Let's look again.
Should be negative 1.
Negative 1, there we go. Keanu, are you okay with that? Okay. You had the look of confusion on your face, but maybe you're just trying to read my writing. All right, here's the last one. This one's super tricky. All right, totally unprepared for this. Integral from 2 to 2 of f of x dx. You guys are so smart. All right, so what was your logic for that? You're right, it is 0. How did you come up with 0? Okay, so you're thinking like a triangle. The height is 1 and the base is 0, right? Okay.
We're talking about like displacement, or not displacement area or whatever. It's not just traveling at all.
Oh yeah.
0.
If I think of this as a velocity function, how far did I travel from time 2 to time 2? I haven't gone anywhere yet, right? Geometrically, I could say that kind of corresponds to, I'm just looking at this line under there. Like, what's the area of that line? Well, it's a line, it doesn't have area, right? There's lots of different reasons why I can like make a logical deduction that the answer is 0. That's good. Everyone all right with all that? All right, there is a theorem in your book that I will show you. We're not going to write it down per se. I'm not going to write down in my notes here, but I'll just show it to you to say that this is the theorem that talks about properties of definite integrals. And most of this stuff, well, 3 of the 5 have common sense kind of things to it. And then a couple others that are 2 you have to think about for a second. So the first one is what we just talked about. The definite integral from A to A is just 0. There's no area under the curve. The second one is that complicated mathy thing that says, if I break up a region into 2 subregions, total area is equal to the area of the subregions. If I go from A to B, then B to C, that's just like going from A to C and finding area. Everyone all right with that one? We're going to skip to the last one. The last one is the other one that kind of makes sense from geometry. This one says, take a region, a geometric region, but now multiply it by K. That has the effect of a vertical stretch. Let's say K equals 3. I'm going to take whatever geometric shape I had, and I'm going to stretch it vertically by a factor of 3. How much has the area grown then by?
3 times.
A factor of 3, right? Whatever the old area was, I stretched it by a factor of 3, new areas 3 times. So this says, scale the function by a factor of 3. That's the same thing as scaling the area by a factor of 3. That'll come in handy later on. Yep.
Is there a situation where the x-axis would be?
We don't actually do that. You could. And but the trick with that is when you scale the x-axis, you now have to change your bounds in an appropriate way, and that gets complicated and convoluted. It is written down somewhere the right way of handling that, but in practice you need it so little that we don't really mess with it. But it's a good question. It's like a natural thing. I just did vertical. What about horizontal, right? 3 and 4. Well, 4 is also got a geometric sense to it, which basically says if I have two different functions and I add them together, how does that area get stacked up? It turns out that the area that you had under each function separately, when they stack them together, that area gets stacked up too. So the total area under the sum of two functions is the area under the one plus the area under the other. And you can draw enough pictures, you can convince yourself that that's right. And then number 3 is kind of a weird one. And the way that we're going to justify this, one way we can justify it, and the book makes reference to this, that it actually kind of makes this part here work out well, in short. It helps out. The other way of thinking about it, though, is this dx is actually referring to like a small amount of horizontal change. As I go from A to B with the understanding that A is smaller than B, my lower bound is usually less than my upper bound, hence lower and upper kind of thing. And so I'm progressing with this positive change in x from my lower bound to my upper bound. But if I start with my upper bound being smaller than my lower bound, then you're kind of progressing from a big number down to a small number. Dx takes on a negative value, and I get this minus sign out front. We'll play with it every once in a while. You have a homework problem or two probably that references it, but we'll check into it more later on. All right, so we're good so far. All right, at about this time last class, a student asked a question that was actually relatively in line with what I was going to cover anyway. So we're going to ask that same question here on a new slide. And our new question is, what about other stuff that's not like straight lines and stuff, right? How do I find those kinds of areas? So here's a quick question. What's the integral? What's the definite integral from -4 to 0 of the square root of 16 minus x squared dx? Yeah, 16 minus x squared.
This type of problem, can you take break up to be you basically you make like 4 different ones where it's going to be like -4 in fraction and -3 and then -2. Is that different problem?
That's a different kind of thing. I think you're probably talking about numerically approximating it, maybe. Okay. So at the moment, I've only told you one way of evaluating a definite integral, right? Which was basically look at a graph and find areas, right? So the question again here is, what is that thing graph? What's the graph of the square root of 16 minus x squared? So the square root in general does this kind of thing. It's like a parabola on its side. This one's a little bit different because it's not square root of x, it's square root of x squared in some sense. There's a little bit of a difference there. Anybody recognize this one at all? It is. So what happens if I said this is a function y, right? If I said y is equal to the square root of 16 minus x squared, I want to understand this better, so let's get rid of the square root part. Y squared is equal to 16 minus x squared. X squared plus y squared equals 16. Does that look familiar? That's a circle of radius what? 4, centered at the origin, right? 0, 0. And because I have the square root, it's the top half of this of the circle, whereas negative square root would give me the bottom half. So I can graph this. This is -4, this is +4, this is also 4. It looks like this. And what part of my half circle do I want? From -4 to 0, this little part over here, right? So this is going to be equal to, what's the equation for the area of a circle?
R squared.
Pi r squared, right? Pi r is 4 squared. And how much of this do I want?
1/4.
I want a quarter of my circle. Oh. That's going to be equal to 4 pi. All right. That's doable, right? Anybody have questions about that? Let's try another one. What about the example integral from 0 to 4 of, I'll write it this way, x times 4 minus x dx. But I could also write that as the integral from 0 to 4 of the quantity 4x minus x squared. The first way that I wrote it really highlights the fact that my function is 0 at 0 and 4. So it looks something like this. It's a parabola, right? Everyone have a good grasp of what the problem is? Question is, what's that area? Now, here's the deal. Before Newton and Leibniz, this is where people got stuck. They're like, it's just a parabola, right? It shouldn't be that hard to find areas. Now, I'll give you a small caveat. Truth be told, they were clever enough that they could find areas under lines. Okay, we got that. Under circles. Okay, we got that. Under parabolas. They actually had a geometric trick that they understood, like, okay, if you have a parabola, you can do this to find areas related to parabolas. Okay, good for them. But beyond that, they were kind of stuck. Like, I know that if I have some sort of velocity function that follows this parabolic behavior, I know that the area under the curve will tell me my displacement. I just don't know how to find that area. I can approximate it. I can fill it in with a grid of lots of little squares and count up squares and make some approximations. This is roughly half a square, all that kind of stuff. I can make approximations and I can get decent approximations, but I don't know how to arbitrarily actually come up with the right answer. That's weird. And they were stuck. And this is where Newton and Leibniz come into play. All right. Newton and Leibniz are going to be able to combine for us what we learned in 5.1 and what we're learning here in 5.2. In 5.1, you saw this notation. When you did indefinite integrals and antiderivatives, you had this notation, but you didn't have a good reason for why you had that notation. You were told this shape here is just an elongated S. Do you know why it's an S? They chose it though because of what? For what word? Sum. Why in the world do the antiderivatives get represented by an S representing sums? That makes no sense. When you get to definite integrals, I look at that notation like, okay, I want to use the word sum. Well, we're talking about total area, so you're summing up areas. Okay, I kind of see that. I'll buy that maybe. Okay. I still don't see how that ties in with indefinite integration. And what's going to come for us, though, is that the indefinite integral is going to marry for us this idea of the definite integral and the indefinite integral are going to get tied together. I can use indefinite integrals to evaluate definite integrals. It's pretty slick, pretty powerful. This is why one of the reasons why Newton and Leibniz get famous, one of the reasons why their calculus turns into just calculus that we study. And that's where we're heading next. Everyone all right with all that? I'll show you something real quick. Need to open up a new program. There's this thing called Mathematica. New share. Does that have an option here? Not yet. Hang on. Oops, I stopped sharing. Let's try again. Oh, Mathematica. There we go. Share. New document. Okay, I'll try one more time. So Mathematica is really powerful. When you first use it, in the world. All right. Oh, I'll try this. I can type. If I click in here and click at this little plus sign right there and do the freeform input, I can try something like this: plot sine of x in red, and then it's going to think for a second, and then yeah, that's cool, right? Mathematica is super precise. I should stop recording because this doesn't really matter. So here we go.